In the first part of week 1, we learned the kinematics equations of planar translation and rotation about a fixed axis. It is relatively easy to adopt these equations to determine the velocity and acceleration of a rigid body undergoing planar translation or rotation about a fixed axis. In the second part, we will start the analysis on general plane motion. There are three methods. The first is absolute motion analysis. The second is relative motion analysis. Both these two can be used for determining velocity and acceleration as well. The third one is instantaneous center of zero velocity. It's IC method. This can be used for determining velocity only. Two or more methods may be applicable for a certain problem. However, they have various difficulties. We will see the easiest one for velocity analysis is IC method, while relative motion analysis is most useful for acceleration analysis. In week 1, I will introduce absolute motion analysis. Relative motion analysis and instantaneous center of zero velocity will be discussed in week 2 and week 3 respectively. Absolute motion analysis can be conveniently adopted to determine the velocity and acceleration of a rigid body undergoing general plane motion. It can also be adopted to relate the motion of one rigid body undergoing either rotation about a fixed axis or translation to the motion of a connected body undergoing general plane motion. This sounds abstract. Let's see some examples. Firstly, how to use absolute motion analysis to determine the velocity and the acceleration of a rigid body undergoing general plane motion. Here shows a very typical example, and here you can see a disk is rolling on this surface to left side. In this one here, it tells you it rolls without slipping. So this means no slipping occurs between this disk and the surface. In the first part, we already know. For a rolling problem, if no slipping occurs, then rolling is a general plane motion. Both translation and rotation about a fixed axis are involved. Okay, now let's have a look. The moving paths of 5 different points on a rigid body undergoing rolling without slipping. Here 5 points from top to the bottom. The first point, the second point, the middle point. The middle point you can see its moving path is a straight line, and this middle point is the circle center. The second last one and the bottom one, the contact point. Now let's do absolute motion analysis. The initial position of the disk is here. Its center point, the circle center point, is at G. After a time increment dt, the disk rolls to a new position here. The circle center point moves to G prime. If no slipping occurs, we know the distance from G to G prime must be equal to the length of the arc A prime B. The length of arc A prime B can be calculated using the radius of this disk r times this angle theta. So we have SG is equal to r theta. Now we do time derivatives on both sides. On the left side, it will be dsg dt, and this can give us vg. On the right side, it's dr theta dt. R is a constant, so we can rearrange this. Now we get r d theta dt. D theta dt gives us omega. Now we do time derivatives on both sides of this velocity equation. On the left side, we have dvg dt. This gives us ag. On the right side is dr omega dt. Again, it can be rearranged to r d omega dt. d omega dt gives us alpha. And here, Vg is the velocity of the circle center point G. Omega is the angular velocity of this disk. Ag is the acceleration of point G. Alpha is the angular acceleration of the disk. So here you can see absolute motion analysis is a direct method. It only involves scalar calculation. The knowledge of trigonometry and calculus are significantly used. Here is another example. We talked about this in the first part of week 1. We know when this bar slides down against the wall, this motion should be a general plane motion. Using trigonometry, we can find the relationship between xa or yb and this angle theta. Then we can do time derivatives on both sides of equation 1 and equation 2. Then we can work out the relationship between VA and the angular velocity theta dot. Theta dot is angular velocity omega. And we also can work out the velocity of point B, VB, and theta dot. Theta dot is the angular velocity of this bar AB. Do time derivatives on both sides of equation 3 and equation 4. We can find the relationship between AA, the acceleration of point A, and theta double dot. Double dot, that's the angular acceleration of this bar AB. And also the relationship between AB, the acceleration of point B, and the angular acceleration of this bar AB. So this is the absolute motion analysis used in this problem. Now, let's look how to use absolute motion analysis method to relate the motion of one body undergoing either rotation about a fixed axis or translation to the motion of a connected body undergoing general plane motion. The connected body may undergo rotation about a fixed axis or translation because rotation about a fixed axis or translation, they are actually the special cases of general plane motion. For example, in this mechanism, crank AB undergoes rotation about a fixed axis through point A. The connected piston C undergoes translation. The relationship between the angular displacement of crank AB and the displacement of piston C can be easily found using trigonometry. So the relationship between the angular velocity of crank AB and the velocity of piston C can be determined. As similar as this, the relationship between the angular acceleration of crank AB and the acceleration of piston C can be determined as well. This mechanism has an application in engine.
Today, the internal combustion engine is used in motorcycles, automobiles, boats, trucks, aircraft, ships, heavy-duty machinery and power generators. A four-stroke engine is an internal combustion engine in which the piston completes four separate strokes: intake, compression, power, and exhaust during two separate revolutions of the engine's crankshaft and one single thermodynamic cycle. Let's take a look at the basic internal parts of a four-stroke engine. Inside the engine block, there is a crankshaft. Piston rods are attached to crankshaft. Pistons are attached to the piston's rods. As the crankshaft turns, it causes the lifter to make each piston move up and down. At the top of the crankshaft there is a camshaft which is connected to the crankshaft by a timing belt. While the crankshaft is making the pistons move up and down, the camshaft is turning, making the valves to open and close. Let's now take a look at how the combustion creates piston's motion. First, intake stroke. The inlet valve is opened, and the fuel-air mixture is drawn in as the piston travels down. Second, compression stroke. The inlet valve is closed, and the piston travels back up the cylinder, compressing the fuel-air mixture. Just before piston reaches the top of its compression stroke, a spark plug emits a spark to combust the fuel-air mixture. Third, combustion stroke. The piston is now forced down by the pressure wave of the combustion of the fuel-air mixture. The engine's power is derived from this cycle. Fourth, exhaust stroke. The exhaust valve is opened, and the piston travels back up, expelling the exhaust gases through the exhaust valve. At the top of the stroke, the exhaust valve is closed. This process is repeated. What had been presented is the cycle of operation of one cylinder of a four-stroke engine. Generally, engines have two or more cylinders acting in concert with each other to produce the engine power.
Okay, next, let's have a look to solved example problems with animation. The first example here is a Scotch yoke mechanism. And here there is a wheel. This wheel has a rotation about a fixed axis through point O. And a yoke. This one can only have rectilinear translation. So obviously you can see the motions can be related to each other. And here the task is to determine the velocity and the acceleration of point B on the yoke in terms of theta. This can be solved using absolute motion analysis. We can establish the relationship between position of point B on the yoke to we can establish the position of point B and theta. Theta is the angular displacement of this wheel. Position B represents the displacement of this rock. So using trigonometry, you can see this xb from O to B. This is equal to r, the radius of the wheel, times cosine theta, plus a constant from here to here. That's the length of this yoke. Okay, we can do time derivatives on both sides. On the left side, dxb dt can give us Vb, the velocity of point B, and that's actually the velocity of the yoke. On the right side, we can have angular velocity, omega, and this omega is the angular velocity of the wheel. In the problem, we already know it's a constant, it's omega O. We can do time derivatives on both sides of this velocity equation. Then on the left side, we will have dvb dt. This will give us AB, the acceleration of point B. That's actually the acceleration of the rock. On the right side, we can work out alpha. Alpha is the angular acceleration of this wheel. Okay, so here, this one will be the acceleration equation. Next example here shows a quick draw mechanism, and this mechanism can produce a slow cutting stroke but a rapid return stroke. Absolute motion analysis, we will use chain rule in calculus. This chain rule was learned in mathematics. Okay, now let me solve a problem in this slide. In this problem, look at this diagram. In this mechanism, there is a cam, and this cam can have a rotation about its fixed axis through point O. O is not the circle center. Circle center is point A. This cam contacts a rod here. The contact point is point R. At the left side of this rod, there is a spring. Because of this spring, This rod can always contact this cam when this cam has a rotation. Here, the angular acceleration alpha and angular velocity omega of this cam have been given. The task here is to determine the velocity and acceleration of this rod when the cam is in an arbitrary position theta. Theta is here. Define the problem. We know the rod undergoes rectilinear translation. The cam undergoes rotation about its fixed axis through point O. Next, we can collect data, and we need a diagram. For this problem, I will use the diagram in the slide. Okay, look at this problem. I can define the fixed origin at point O. I can define a positive direction along x direction. For my convenience, this positive direction along x direction is to the left side. In this problem, alpha, omega, and theta of the cam have been known. What's unknown is Vr and Ar. Vr is the velocity of the rod. Ar is the acceleration of the rod. Using absolute motion analysis, I need to establish the relationship between xr and theta. xr is the displacement of the rod. We can find the distance from O to R, that's xr, should be equal to 2r times cosine theta in this triangle A, B, O. From B to C, that's r times cosine theta. From C to O, that's r times cosine theta. Okay, now, after getting the equation of displacement, then we can do time derivative on both sides. On the left side, dx dr gives us Vr. On the right side, for this time derivative, we need to use chain rule. 2r constant. We don't need to worry about these two. For cosine theta, it will become negative sine theta. Theta here is a variable. So next we can do d theta dt. d theta dt gives us omega. Do time derivatives on both sides of this velocity equation. On the left side, dvr dt gives us alpha r. On the right side, In this time derivative, we will use chain rule again. Two are a constant. Firstly, we fix omega, do time derivative on sine theta. And here we get cosine theta times d theta dt. D theta dt gives us omega. Next, we fix sine theta, do time derivative on omega, d omega dt, d omega dt gives us alpha. Okay, now you can see we can use these three equations to express the relationship of the displacement of this rod and the angular displacement of the cam. The relationship of the velocity of this rod and the angular velocity omega of this cam and the angular displacement of this cam. And finally, the relationship between the acceleration of this rod and the angular acceleration of this cam, angular velocity of this cam, and the angular displacement of this cam. So that's the results we obtained using absolute motion analysis. Absolute motion analysis is direct and easy to understand. It may be adopted if the geometric configuration of the problem is not complex. But if the geometric configuration is complex, absolute motion analysis may involve complex calculation. This is not preferred. In this case, relative motion analysis can be more convenient than absolute motion analysis. We will study relative motion analysis in next week.